So this session basically is about the security enhancements in JDK 9. As you know, in JDK 9 we have a lot of cool new stuff like JShell, the new module system, new process API, multi-release jar files, and a few other cool stuff. However, we also have quite some interesting security enhancements that we'll cover in this session, and we'll provide some background information for you to understand what are these enhancements about and how you can use them in practice. So just before we start, who I am, my name is Martin. I'm working as a Java freelancer. Just recently I wrote a book on RabbitMQ. So if someone of you is using RabbitMQ or is interested in any kind of message brokers, we can have some discussions after the session. I'm also one of the guys who organizes the events of the Bulgarian Java user group. And this month we also have our own community conference called JPrime. And I'm also a very big OpenJDK enthusiast. You can follow me on Twitter. I tweet mostly about Java and Java conferences. So in this session, just before we dive into the new security enhancements in JDK 9, we'll cover what is the current state of TLS support in the JDK. And most of these enhancements in JDK 9 are enhancements around the support for the transport layer security protocol in the JDK. Then we'll move to one of the most major enhancements in JDK 9, which is called DTLS. DTLS is Datagram Transport Layer Security Protocol, which is basically TLS over UDP. Then we'll cover another interesting extension in JDK 9, which is TLS Application Layer Protocol Negotiation Extension, which allows you to negotiate the application layer protocol during the TLS Handshake process. And at the end, we'll cover the rest of the security enhancements at a glance. We have some more interesting security enhancements in that section. So just before we discuss the security enhancements, let's see what's the current state of TLS support in JDK. Up to JDK 9, we have support for TLS 1.2 and earlier versions in the JDK. And this support is provided via the so-called JCCC API, or Java Secure Socket Extension API. You can think of that API as an extension of the standard socket mechanism in Java, which basically enables you to communicate between a client and the server in a socket manner using TLS. Currently, there is specification version 1.3 of the TLS protocol currently ongoing. And just a few weeks ago, the Oracle security team announced that it started support implementing new features around TLS 1.3. So we should expect to see some new enhancements around TLS in upcoming versions of the JDK. And as most of you know, TLS is typically used to secure most types of application protocols. Another interesting use case of TLS is to provide the possibility to establish the so-called SSL VPN type of communication when you try to connect to your corporate network. So basically, TLS is the de facto standard that allows you to secure the communication between endpoints. It's, of course, a predecessor, successor of the SSL series of protocols. And just before we understand what are the security enhancements about, we need to understand how does the TLS handshake process work. This is the first step that is established before two parties can start communicating and exchanging messages in a secure fashion. So the first thing that happens in the TLS handshake process is that the TLS client sends some message to the TLS server saying, okay, this is my TLS version, and these are the cryptographic chiffres that I support. This happens at step 1. At step 2, the server gets that information from the client, determines which are the chiffres that the server also supports and are supported by the client, negotiates the TLS version that will be used with the client, and returns the public certificate of the server to the client. And the public certificate, in fact, contains the public key of the TLS server. At step 3, when the client gets the public certificate and the negotiated information from the TLS server, it gets that the information from the public certificate and optionally verifies that information against a list of known certificate authorities. This process is called certificate revocation checking, and it can be done in several ways. One of the ways is that the certificate authority publishes a list of certificates that are revoked. Or another way is that the certificate authorities provides implementation of the OCSP protocol that is used to validate the certificate from the client. So when the client validates the server certificate, at step 4, the client may optionally also send its own public certificate to the TLS server, and this is required if we want to establish bidirectional communication between the client and the server. When the server gets the client certificate, at that point, the client also generates the so-called shared secret key using the security information negotiated with the server. And that shared secret key is used, in fact, to encrypt the communication between the client and the server. And when this happens, basically, the client and the server exchange additional messages which identify that the TLS handshake process is done. And the actual communication of an exchange of secure messages may start happening. So this is basically the TLS handshake in a nutshell. Now, having considered that, as we said, in the JDK we have the JCCC API which provides implementation of TLS, and behind the scenes it implements that TLS handshake flow. So the Java Secure Socket Extension API has a default implementation provided by the Sun JSSC provider. And why I'm telling you that this is a provider, basically most APIs in the Java Security SDK are implemented as provider APIs, meaning that you can plug different implementations of different cryptographic algorithms, and the same applies for the JSSC API. And core classes of that API are provided by the javax.net and javax.net.ssl packages. It provides two modes of operation. Blocking mode, which is the more straightforward one to use. It's very similar to how you would establish a socket communication between the client and the server. However, you need to specify some additional information for the TLS handshake process. And the more complex manner of communication is the non-blocking mode of operation of JSSC. And there is a wrapper class which simplifies the communication with HTTPS endpoints, which is provided by the JavaX.net SSL HTTPS URL connection class. And this is the JCCC blocking mode of operation. It's provided by the SSL socket class. It is used in the same manner as a regular socket, as we said. And the handshake process might be triggered in several steps. First, you might explicitly call the start handshake method on the SSL socket instance that you have created either on the client or the server. Or behind the scenes, if you try to get the current TLS handshake session, and TLS handshake hasn't happened yet, it is triggered by the client or the server by calling the getSession method. Or the third way TLS handshake might be triggered by the client or server is if you try to read or write to the socket. And this is a simple example of how JCCC blocking mode works. First, we set two properties which identify, this is in fact a snippet that identifies the SSL server. We first specify the key store which stores the public certificate of the server. This key store may have some password. Then we use a utility called SSL Server Socket Factory that is used to create the SSL server socket. In that particular example, I create the server socket on port 4444. And as you might guess, when I try to call the accept method in that case, this is a blocking operation. And that's why we say it's the blocking mode of operation. It's very similar to how standard sockets work. So this operation blocks until we get some information from the other party. Then we get a reader from that socket. We read the information that is received by the server. And then optionally, we provide some response back to the client. And at the end, we make sure that we close the socket. And this is how TLS client looks like. Again, we use another factory called SSL Socket Factory to create the client SSL socket. Before that, we set the trust store for the client, which basically stores information about the certificate authorities that are trusted by the client and that are used to check the public certificate of the server. Then we get a writer from the client socket. We send some information to the server, and we read back the response from the TLS server. And in the end, we make sure that we close the client socket. As you can see, basically, this is very straightforward to how you would establish standard socket communication with some more additional information. And the non-blocking operation of JSSC is a bit more complex. It's provided by an API which is not so well known to the Java community. It's called the SSL Engine API. And the way it works is by, when you try to write something to the network, you first write that information to the so-called application byte buffers which reside on the application side. And this happens when you call the wrap method. Using those application byte buffers, the information is sent to the network byte buffers, out of where it is sent over to the network. And when information is received from the network using the unwrap method. It is first received by the network byte buffers and written to the application by byte buffers, from where the application then handles it. And basically, if you try to call the wrap and unwrap method and TLS handshake process hasn't happened, it is triggered behind the scenes for you. Or you can explicitly trigger it with the begin handshake method that can be called on the SSL Engine instance. As we said, it's much more complex than the standard SSL socket API. And we have two additional options that allow us to debug what's happening between the client and the server when they establish the TLS handshake process or when they start exchanging messages in a secure fashion. This property, javax.net.debug, is quite useful if you want to see what happens during the TLS handshake process or when messages are exchanged between the client and the server. And it's quite configurable. For example, you might say only handshake as a value, which says that you want to see only the messages that flow between the client and the server during the handshake process. Or you can say SSL. You can see the messages that flow only during the actual exchange, but not the handshake. Or you can combine both with the old value. Now, this is about what we have before JDK 9 up to JDK 8. Now, in JDK 9, we have something called DTLS introduced. And DTLS essentially is Transport Layer Security Protocol over an unreliable protocol such as UDP. By default, TLS runs over a reliable protocol such as TCP. However, many applications such as chat servers or DNS applications require also secure communication, which needs to be established by means of DTLS. And also, one interesting thing about the DTLS specification is that it follows closely the versions of the TLS specification. So there is currently version 1.3 in draft mode, which would be at some point supported by the JDK. So at that point, the JDK provides support for TLS 1.2 and earlier versions. And there are a few differences between DTLS and TLS in terms of protocols. First, in DTLS, we have a new field added to the protocol, which is an explicit sequence number. And the reason for that field is because we don't have a guarantee of the order of messages that are exchanged between the client and the server. And this comes by the nature of UDP. There is also some dropped support for cryptographic chiffres, such as RC4. All of the chiffres that are not supported by DTLS are described in the security documentation provided by Oracle. We also have another field called retransmission timer added to the protocol, and that's used to retransmit packets that have failed to be sent over the network. You know that UDP is an unreliable protocol, and we need to have some additional mechanism to guarantee that we need to redeliver messages if they have failed. And there are two other differences. One is that MAC verification failure triggers warning instead of failure in DTLS, and we have a new request message added to identify the sender, which are of less significance. And if you want to use DTLS before JDK 9, you have several options. You can either go with the Bouncy Castle Java Secure Socket extension provider. How many of you have used Bouncy Castle as a library? I see 4 people, okay, 4 or 5 people. So Bouncy Castle, as you might know, is one of the standard providers of security API implementations for JDK. And Bouncy Castle provides a very straightforward to use DTLS implementation. Another way you can interact with the DTLS protocol is using an external library such as OpenSSL through JNI. And you can use DTLS through Java like this as well. And in JDK 9, basically, they have introduced support for DTLS 1.2 and 1.1. Implementation is adapted to the JCCC API that we saw currently, which means that minimal set of changes was introduced basically to provide implementation for DTLS. However, this has quite some drawbacks, and one of the main drawbacks is that this API is fairly complex to use at that point. And one of the reasons for that is that the SSL Engine API, which provides the non-blocking operation of JCCC, is used to adapt the DTLS implementation too. There are some also implementations that are done by default behind the scenes. So order delivery of messages is provided automatically for you by the SSL Engine class. During the TLS handshake process, we cannot afford to lose messages. So for that reason, in the JDK, during the handshake process, redelivery of messages is automatically done behind the scenes. However, if during the actual exchange of messages between the client and the server, delivery is not guaranteed. So you need to make sure that you redeliver failed messages. And also the sequence, the proper order of delivery of messages is not guaranteed, as we said in UDP. And for the purpose of handshake, it is done behind the scenes. And also it's done when you exchange messages between the client and the server by default. And in order to get started using DTLS in JDK 9, first you need to get an SSL context, which basically is the starting class that is used to create SSL Engine instances. You get an instance of DTLS as an SSL context. You initialize it with some additional parameters, such as what is the key store, what is the trust store, and so on. And then you create an SSL Engine instance out of that context, and you specify whether that's an SSL client or server using the setUseClient mode method. And currently there are no good documentation and full documentation about how you can fully understand what are the corner cases of using DTLS in JDK. However, there are some nice unit tests provided by the OpenJDK 9 test suite, which you can review, and you can use them as a starting point for DTLS. And during the demo, we'll see shortly how it works. Another more interesting extension and simpler to understand is the TLS ALPN extension. And basically, ALPN, or Application Layer Protocol Negotiation extension, is used to identify the application protocol during the TLS handshake process. It also allows the TLS server to send different public certificates based on the negotiated application protocol. And one really good use case of this is now with the upcoming version of the HTTP protocol. As many of you know, now many web servers start supporting HTTP 2.0. However, there might be some clients that are still running on HTTP 1.1. So if you try to establish SSL communication with a web server that supports HTTP 2.0 and HTTP 1.1, based on the negotiated version of the HTTP protocol, you might send different public certificates to the client. So now the TLS process is aware of which application protocol is negotiated between the client and the server. That's basically it. And to enable ALPN, what you need to do is, from the SSL socket or SSL engine instance that you have created, depending on which mode of operation of JCC you use, you get the so-called SSL parameters instance, which basically is a wrapper for the SSL parameters used by this socket or engine instance. And you call the setApplicationProtocols method, where you specify a string of the names of the application protocols that are supported by the TLS client or the TLS server. When you do that, the TLS handshake process is triggered between the client and the server, and during that process, the application protocol is negotiated. And when that protocol is negotiated and we have a TLS handshake established, you can get the negotiated protocol by calling the getApplicationProtocol method from the SSL socket or engine instance. And as you see, basically, here we use just an array of strings to identify what is the negotiated protocol between the client and the server. However, we have a much more complex way to negotiate the application layer protocol. And for that reason, we need to call the SetHandshake application protocol selector method, which basically is called during the TLS handshake process to determine the protocol. And it basically accepts a lambda, which receives two parameters, the SSL server socket and the list of client protocols suggested by the TLS client. And here in this particular example, we get the current SSL session from the server socket, we get the negotiated cryptographic cipher, and we get the current packet buffer size that's negotiated between the client and the server. If the cryptographic cipher is RC4 and the packet buffer size is bigger than 1024 bytes, then we return protocol 1, otherwise we return protocol 2. As you can see, this is a bit more flexible way to negotiate the application protocol between the client and the server. And now let's see a brief demo of these things. For my demo, I'll be using a banking application server, custom banking server, which basically provides me with the possibility to create pluggable implementation of different applications. And my banking application server is implemented as a Jigsaw module. So basically, all of my applications are Jigsaw modules. So what I'm going to do now, I'm going to switch. Here, so this is the diagram that describes how is the banking server implemented. We have different application protocols that are supported by this banking protocol. This might be XMPP, SIP. You can imagine that we have different applications running in the bank that provide different endpoints through different protocols. And also we have different applications that are deployed in the banking server. So using that scenario, we'll demonstrate the new features. Switching back to my Eclipse. So if we see how is the banking server implemented, just very shortly. So I basically use the service loader utility, which behind the scenes is used when you deal with Jigsaw modules. And I get all the implementations of the banking application interface. This basically is a service that the banking server provides for applications to implement. So I basically discover all of the applications that are deployed to that banking application server, and I call the execute method, which just runs the application. Oh, sorry. Yep. So, yeah, I just iterate over all of the banking applications deployed in the banking server. And using the service loader utility, I discover all of those applications that implement the banking application protocol. This is an interface, a service interface that's provided by the banking server. And for all of those applications, I just call the execute method, which basically is fairly straightforward. And what else my banking server provides, if I just navigate and see what else do I have, I also have a banking protocol service interface, which must be implemented by all the protocols supported by the banking server. And if I look into the Jigsaw module for my banking server, I see that it just requires one module from the JDK, which is Java logging. It exports some packages that are visible to other modules. And here are the two services that are defined and may be implemented by other modules. These are the banking application and the banking protocol. And if I see a simple implementation of a banking protocol, let's say this is the fixed protocol. I have just one class which is called fixed protocol, which implements that interface. A protocol has basically a name and some logic to execute a packet over that protocol. And if I look into the module info of that protocol implementation, I see that I have a service implementation which is basically provided by the fixed protocol class, and it implements the banking protocol service. Pretty much same applies for the banking applications. I have one banking application which is called demo application. And if I look into this demo application, what it does, it just creates some packet that needs to be sent over the particular protocol. It gets the protocol service provided by the banking server and calls the send packet method that sends the particular packet using the particular protocol. This service here basically discovers the protocol based on all the implementations supported by the banking server and sends the packet over that protocol. Now if I'm to demonstrate how this works, I'll use the fixed protocol here. What I'll do, I'll just need to recompile my demo application module and run it. The banking server has a main class provided by the server class, and as you can see, the demo application is discovered and a packet is sent over the fixed protocol. Now let's imagine that I have some chat application running in the bank, and that chat application basically provides implementation of the SIP protocol, which needs to be secured using DTLS. So if I'm to see how basically an SIP implementation would look like, I'll open the SIP protocol. And here I have a lot of stuff, a lot of code written. The reason for this is because, as I said, the DTLS API is fairly complex to start with, and there are a lot of corner cases that you need to consider during the TLS handshake process, which are not provided out of the box. And basically, most of the stuff here are taken from the OpenJDK test suite, but the essential thing here is to see how we create the actual SSL Engine instance that's used by the SIP protocol implementation. What we do, we do similar thing that we saw on the slides. We set the trust store, which basically provides the list of certificate authorities that the client trusts, in that particular case, the SIP protocol implementation. I get an instance of DTLS using the SSL context. I don't specify any key stores or trust stores here when I initialize that context, and I create an SSL Engine instance. I set some information on the SSL parameters for that instance, and I specify that this is going to be a TLS client. And this is how I create the SSL Engine instance, which is used to communicate the server via the wrap and unwrap methods to write and read information. And if I'm to look into the DTLS server, the DTLS server looks quite similar to the client. And if I'm to look how is basically the SSL Engine instance created, it's created in a much similar way. I specify eventually some key store. I get information for that key store. I get an instance of DTLS. I initialize that context, and I create some SSL Engine instance, pretty much as I do with the client. And here I specify that this is a DTLS server by using the setUseClient mode and specifying it to false. This is how I create an SSL Engine instance. If I'm to run that, it runs basically the DTLS server, and I'll go back to my demo application and change the protocol to SIP. I'll recompile my demo application module and run the banking server again. In that particular case, it sends some SIP packet to the protocol and gets some information that there are no cryptographic ciphers negotiated between the client and the server. In that particular case, I didn't specify any cryptographic ciphers. And now basically you can imagine that there is yet another application in the bank that basically runs the XMPP protocol. And that banking application provides different versions of the XMPP protocol that are supported, and I need to negotiate one of the two. To see how the XMPP server looks like, I'll open the XMPP server. It's a fairly straightforward SSL socket server. And here the main thing is the set application protocols method. As you can see here, set application protocols specifies that my XMPP server supports version 1.1 and 1.2 of the XMPP client. And now I need to specify also the same for the XMPP client. I have an implementation of the XMPP protocol for the banking server. And that implementation also calls the set application protocols method to specify which are the application protocols supported by the TLS client. In that particular case, that's the XMPP protocol implementation. And it just supports version 1.1. If in my demo application I go back and change the protocol here to XMPP, this identifies the XMPP protocol implementation. I need to recompile my my demo application and run it. And I see that I haven't started properly. I haven't started yet my XMPP server. I need to start my XMPP server. And run the banking server again. And I see that the negotiated protocol is XMPP version 1.1. So basically, if in the set application protocols method I specify multiple protocols in the client and the server that are both supported by the client and the server, just one of them is negotiated, and that's the first from the list in either the client or the server that matches a protocol from the other endpoint. Okay, so any questions about DTLS or ALPN in JDK9? No, if not, so basically these were two of the major enhancements in JDK9. However, we have quite some other stuff, interesting stuff going on. And one of them is OCSP stapling for TCP. So basically, this is one more optimization technique, more on the performance side, which basically provides you a way to reduce the number of requests that a TLS client sends to the certificate authority. As you know, every time the client gets the public certificate from the TLS server, it needs to send a request to validate that certificate against the certificate authority. However, as you can imagine, that may imply a lot of requests from the client to the certificate authority. And for that reason, this functionality using OCSP Staplink is shifted from the client to the server. It is the TLS server that does the certificate validation rather than the TLS client. And additionally, it caches the responses from the certificate authority. So in order to enable OCSP Staplink, you need to specify a few properties on the TLS client and the TLS server. For the TLS server, you need to specify the enable status request extension equals true, and the same for the TLS client. And you have one additional property to set on the client, which is called check revocation. Another thing, and that's quite an interesting thing, is that before JDK9, we had the so-called JKS key stores used by default. This was a proprietary Java format used to store information about public certificates. But in JDK9, they decided to introduce a more general purpose key store format, which is provided by the PKCS 12 specification, which is quite a mature specification that defines a format for storing public certificate information. One of the main benefits behind this is that the PKCS 12 specification provides support for a much wider range of cryptographic algorithms on one side. And on the other side, this provides better interoperability between your Java applications and any other applications written possibly in other programming languages that need to make use of the same certificate key store that's used by your Java application. Because this format, in fact, is language independent, which is not the case with JKS. However, in JDK9, we still support the JKS or Java key store format for storing public certificates. And if you want to use it or your applications already use JKS, you don't need to migrate to PKCS 12 certificates. And there is a set of other smaller enhancements. For example, the GHASH and RSA, a series of algorithms, are improved in terms of performance by leveraging some new CPU instructions. Also, SHA-1 certificates are disabled for certificate validation. So if your server sends you public certificates that make use of the SHA-1 series of algorithms, your application will simply not work with SHA-1 certificates in JDK9. And there is also an implementation of the SHA-3 series of hash algorithms provided in JDK9. And also new implementation of the secure random API, which basically is a cryptographically strong random number generator. So as a summary, as we saw, JDK9 introduces a set of significant enhancements in terms of the TLS support, which is provided in JDK9. And in upcoming versions of the JDK, we'll see more enhancements coming with the new specification of TLS, which is 1.3. And this includes also DTLS 1.3. And yeah, of course, hopefully we'll see some more cool new security enhancements coming, not only for TLS, but also cryptographic algorithms and other interesting security APIs. And that was the session. Any questions about TLS security enhancements in JDK? Anything about the security APIs in Java in general? If no, then thank you for attention.